Hello everyone. In this short video, we'll see the some of the basic properties of vector spaces before going to the concept of subspaces and other steps and all. Okay. So as a first property, I'd like to show the cancellation law for vector addition. What does this property says? If x, y, and z are three vectors in a vector space V, and then if V is a if x plus z equal to y plus z, then x equal to y, which means I can cancel this z something like this. This is called as cancellation for vector addition. What is the proof? We can prove this very easily. How do I prove it? It's quite simple to prove it. I know that for every z in V, then there exists minus z in V such that z plus minus z equal to 0. Is that correct? So why don't I start with x, and x can be written as x plus 0, and then this x plus 0 can be written as x plus z plus minus z, which comes from here, and then I can use the associative property to associate these two, which means x plus z can be clubbed something like this, and then x plus z is equal to y plus z has been given, so that I can use here. So that is y plus z and plus minus z. Again I can use my associative property, which gives me y plus z plus minus z, and that gives me y plus z plus minus z is 0, and that's equal to y, which means x equal to y. So I have used that x plus z equal to y plus z in the middle, which means if x plus z equal to y plus z, then that x is nothing but y itself. That's what I have proved, which means I can cancel this z on both sides. Okay. Followed by this property, we can prove some of the other well-known properties as well. One of them is here. The zero vector in the vector space is unique. How do I prove that? Proof. Suppose there exist two zero vectors. Say, for example, 0 and 0 prime as two zero vectors. Then what does that mean? For every z in V, I know that z plus 0 is also z, and then z plus 0 prime is also z, because 0 is a 0 vector, 0 prime is also a 0 vector. Now how do I prove that this 0 vector must be unique? Now you know that this z and this z are same, so therefore these two must be same. So these two together implies that z plus 0 must be same as that of z plus 0 prime. Now just in the previous slide I have proved that cancellation law is true for vectors, which means I can cancel out the common numbers over here, and therefore this 0 must be same as that of 0 prime. So that proves that if there is two 0 vectors present, then both should be same. Therefore the 0 vector in a vector space is always unique, right? Not only this, if you see the additive inverse of any vector, then that also must be unique. What is the proof? That is also very simple to prove. Suppose u belongs to V. Now question is, this must be unique. Additive inverse must be unique. Suppose by contrary, that assume that there exist V1 and V2. There are two inverses such that u plus V1 also giving me 0 vector, and then u plus V2 is also giving me 0 vector. Right? That's the definition of additive inverse. Now again, by cancellation law, what you can do, you can compare these two quantities, and then u and u are definitely same. Therefore you can cancel this out and then say that v1 must be same as that of v2, which means if there are two inverses, then both inverses must be same, which means any additive inverse of a vector must be same as that of the other one, which evidently says that additive inverse of a vector space, additive inverse of a vector in a vector space must be also unique. Okay. So these are the vector addition properties. There are some properties with respect to scalar multiplication as well. If you see the 0 times of v, and that must be 0 for all v in v. How do I prove that 0 times of v must be equal to v for all v? It's so simple to prove. I can write 0 times of v as 0 plus 0 times of v. Is that correct? Because 0 is nothing but 0 plus 0, the additive inverse property. And that further I can write it as 0 times of v plus 0 times of v, because distributive property on the scalars is also there, because this 0 can be considered as a this 0 is nothing but the scalar 0, and therefore this is 0 times of v equal to this. And without worried about much, I can also add one vector 0 over here. That is not going to affect, because 0 times of v is anyway is a vector, and then the 0 vector must add it. That should again give me 0 times of v only. Now again you can use your cancellation law and then see that these two quantities are same, so therefore this and this can be cancelled, 0 times of v and 0 times of v, and that gives me 0 equal to 0 times of v. So 0 times of v must be equal to 0. So this is true for every v in v. So that proves this. Also, you can say this property is also holds. What does that mean? The minus a times of v is same as that of writing minus of a times of minus v. We use this in our real life without noticing that actually this is a application of, or this is a property in vector space. How do I prove this property? So proof. We know that 0 times of x is equal to 0, not x. 0 times of v is equal to 0 for every v, just we have proved in the previous one. Now 0 can be written as minus a plus a, because 0 is the scalar and that's the additive inverse, additive identity for scalar field, and that's equal to 0. And now I have the distributive property, therefore minus a times of v plus a times of v is equal to 0. And that says that the inverse of av is actually minus a times of v. That's what it shows. And I know that the inverse of av is unique. And in the other side, I know that the inverse of av must be same as that of minus of av from the property of vector space. And therefore, minus of av is same as that of writing minus a times of v. Correct? In particular, one can say that minus of, instead of a, if I write 1, then minus 1 times of v is equal to minus 1 times of v, right? That is there. Minus of 1 times of v is equal to this. And I know that 1 times of v is actually equal to v itself. So therefore, minus v is equal to minus 1 times of v, or minus 1 times of v is equal to minus v. That's what I know this, right? Minus 1 times of v is equal to minus v. Now let's see what about this, the other part. So the a times of minus v, that can be written as a times of minus 1 times of, because minus v is actually minus 1 times of v. So that one. And then I also have the scalar associative property, if you remember, alpha beta times of v is actually can be written as alpha times of beta v. And if you use that property, then what will happen? I can club these two, so that gives me minus a times of v. Correct? So that's what I wanted, right? So minus a times of v is same as that of a times of minus av, and minus a times of v is also same as that of minus AV. So this is my 1 and this is my 2. So from 1 and 2, what I can conclude is minus A times of V is same as that of minus of AV, and that minus of AV is minus A times of V, that is same as that of A times of minus V. So all are same, correct? So that proves this part. So there's one last property which I want to prove it is A times of 0 vector is always 0 vector for every A in F, right? The 0 is coming from the vector field. How do I prove it? I know one thing, A times of 0 plus 0, all are vectors, 0 vector plus 0 vector, is nothing but the 0 vector. That's what my A times of 0 vector. And that can be written as A times of 0 plus A times of 0, because I have the distributive property of scalar among the vectors are present. So now one can do that. So I can say add this 0 here without any problem, and that shows that this number and this number can be cancelled by cancellation law, and that proves that these two must be same. So 0 must be equal to A times of 0. So that says that A times of 0 is always 0 for every A in F. Okay. So that's all about some of the basic properties of vector spaces before going to subspaces. So in the next lecture we'll discuss the subspaces. Thank you. We'll see you in the next lecture.